consider another example of simple harmonic motion, which is what our mass spring system. Your mass spring system. Now we said we have different systems that undergo simple harmonic motion. We've discussed simple pendulum, we've discussed what torsional pendulum, and now we want to consider what mass spring system. Now from what we have here, for your mass spring system, we have a spring attached to a mass, and this spring is also attached to the wall. Now what happens here is when you move this mass forward, when you move the mass forward and lift it, what happens? You are going to see a to and fro movement, until the movement fades off. Am I communicating? Now, what are you seeing? You can see what force is applied to your spring, and what happens? That spring is giving you what? A displacement. So in essence, you simply have the force is directly proportional to what? Displacement. Remember, you have a proportionality sign. Elementary maths will tell you, removing your proportionality sign, you will add what? A constant and what? An equal to sign. So your F here will simply give you what? Minus S of what? S. Why are we introducing our constant to be S, not K? We are introducing the constant S because what we have here is a spring. And when we are introducing this constant S, your S simply stands for what? Your spring constant. Am I communicating? Now remember, when we are considering force from elementary physics, force is simply what? Mass times acceleration. So recall that force is equal to what? Mass times acceleration. So what do? We can represent MA in this equation. So in this equation, we can say that what? MA will be equal to what? Minus S of S. Looking at this equation is not balanced, it's not simplified. Balance this equation. If you want to balance this equation, what do? You take your minus sign at this side, take it across to your equal to sign to the other side of your equation. Meaning what? A subtraction is crossing an equal to sign, and it will be what? It will be positive. So you simply have MA plus what? S of what? S, and this will be equal to what? 0. Are we done? No. Remember, we have what? Acceleration. We know that acceleration, when we are considering acceleration is what? Acceleration is when you differentiate velocity once. So if you differentiate velocity once, you have what? Acceleration. But looking at velocity, we can still differentiate velocity. And if you differentiate velocity, what do you have? You are going to differentiate what? Displacement. So if you differentiate both, velocity is equal to, we are differentiating what? Displacement once, and we have what? Velocity. So how do you think we are going to differentiate acceleration? Now recall, A can be differentiated to be d square S over what? dt square. If you do this, you will simply arrive at what? Acceleration, meaning you are differentiating what? Displacement twice. Now, why don't we represent what we have here in this equation, where your m multiplied by d square S over what? dt square plus S of what? S, and this is equal to 0. Are you done? No, we are not done. Why are we not done? Remember, when we have a differential sign here, you make your differential sign to stand alone. Making this differential sign to stand alone is you are dividing your equation with what? M. So you are dividing through this equation with M, you are dividing here with what? M, and you are dividing here with what? M. Now if you do that, your M here will simply remove your M here, and you'll be left with what? D square S over what? dt square plus S over M of what? S, and this will be equal to what? 0. Remember, what are you seeing here? You are seeing what? Second differential. Second what? Differential. I told you in our maths class that when we are considering your differential, your second differential, you rewrite your first differential. We can rewrite our first differential to be what? S dot of what we want to differentiate with respect to. But in this case, we are differentiating with respect to time, right? Now, if you want to represent your second differential, how do you represent it? s dot dot of what you are differentiating with respect to. Am I communicating? So what happens is, apply this concept into this equation. If you apply this concept, you simply have that you x dot dot of what t plus what s over m of what s, and this will be equal to 0. What do you think you are going to do next? This is the end of your equation, because there is nothing you can simplify again. That is the physics. Look at what you have here. This is a good example of angular velocity from our simple harmonic motion equation. So basically, this is your what? This is the equation for what? Mass spring system. But when you are asked to connect this equation to your simple harmonic equation, what do? Remember or recall, we talked about square the angular velocity square, and we said angular velocity square is what? K over m from simple harmonic motion. Now, in this case, what do you think your angular velocity will be? In this case, your angular velocity, that's the square of your angular velocity, will be equal to s over m. So anywhere we are seeing s over m, we are imputing what? W square. So your final equation will now be what? S dot dot of what? Of t, s dot dot of t plus w square of what? S, and this will be equal to what? 0. Now, looking at this equation simply gives you what? The equation for what? Simple harmonic motion. So you've been able to prove that what? Your mass spring system is a good example for what? Your simple harmonic motion. Thank you.